Scott model Stereo Master LK-60b. This was actually a kit that was built, and it even has the little label with the person's name on it, because you got this silver tag when you bought these kits that you could sign your name on it and stick it on there to let everybody know who built it. So this was originally a kit and was built. I've never taken it apart, never plugged it in, never tried it. I did show it on the Scott 342 video that I did, and said that I would come back to this, and it is now time to test this one out and possibly do a restoration. Well, curiosity is certainly getting the better of me on this, so before I even try to turn it on or anything, I want to take this thing apart and just see what kind of work was done on it, because some of these things, these kits, when they're built, I've taken some apart and they are like a work of art. Other ones, you can tell it was a beginner that did it, and you know, we had to clean some things up, but you just never know with a kit what you're going to get until you look at it. And certainly we don't know why this got sold. It could be just because somebody wanted to purge some things that they don't use anymore. Maybe it was because something doesn't work on it. But whatever it is, this thing is in such nice condition. I really don't want to damage it any further, so we're going to check it out before we apply any kind of power to it. Okay, and there we go. So our first little thing I notice is that our meter has come loose, and I think it's just held in there by a little clip, and it is. So we'll have to watch that. But let's get in here a little closer. And for a Scott stereo, this heatsink is amazing. Usually on the amplifiers of this era from them, they typically will just use the back of the chassis for a heatsink, but you can see these have real live heatsinks on them. And if I'm not mistaken, they use 4 2N3055 ubiquitous TO3 transistors. So it's a pretty cool design. Everything looks very serviceable, and you can see this looks, so far, the craftsmanship on it looks really good. So before I take the bottom off, I just want to show you some of the really cool features of this amplifier. If you look over here at this label, you actually can switch the function of that front panel meter so that you can set the bias of the amplifier. So it has its own built-in bias calibration meter, which I think is amazing. I mean, that's just really cool that they added that. The other thing is this aluminum box here on the top, and what it does is it's actually isolating the phono stage, which has 3 different levels of sensitivity. So it's kind of neat. Again, this is a very well built little amplifier, and I would have loved to have been able to build one of these as a kit, brand new, when they were coming out. Looking at the power supply, it seems to be relatively simple. Just have a single center tapped winding, full wave rectified. It goes to an unregulated 70 volt source. Then we go through a dropping resistor. We have what appears to be a 27 volt Zener diode, and then a couple more resistor pi networks. And we have a 25 volt source and a 20 volt source, and kind of semi-regulated there. And that's it. So we really don't have a lot to check as far as power supply is concerned, which is good. So let's go up to the unit here. This power cord is like brand new. I mean, doesn't even feel stiff or crusty or anything. It's not going to need to be replaced. Well, one thing I do see, looks like one of these caps down here got lost. So let me see if I have. That's the actual power fuse. It's 1 1.25 amp slow blow. So let me see what I have here, and we'll get that replaced first. Okay, I was able to find a donor fuse socket with the same type of cap, and I do have a 1.5 amp fast blow, but I do not have a 1.5 amp slow blow handy, so we'll have to make do with what we have for now, and then we can always order the appropriate fuse when the time comes. So looking a little more closely at this cap and this cap are the two speaker capacitors for the outputs of the left and right channels. And the center one is the big capacitor for the power supply. And even though it appears as though this is an isolated ground capacitor, going on to ohms and just checking to the chassis, so like if I clip on to, well, this is attached to the chassis, or I was, they do have ground attached to ground, but they're just using this point right here as a star ground, which is nice. That's good. So the construction quality on this is actually pretty good from what I'm seeing so far. The builder did a really nice job. All right, let's plug this in. Let's go to voltage. And I'm going to switch on the power supply, and we are on current limiting right now with a 50 watt bulb or 40 watt bulb, 40 watt. And I have the power switched on. I have a fuse put in. Let's turn this thing on and see if we get any voltage over here. So this is the output of these two rectifiers right here. This is where they come together. They go up the red wire, go right to there. And sure enough, 63 volts. And that's supposed to be a 70 volt supply, and because we have the current limiting bulb in there, I would expect it to be lower than that. There is absolutely no filament glow, hardly at all visible on the bulb, so it's very minimal current draw. So at least we know there are no shorts, and we have voltage. Now let's see how fast, when we turn this off, how fast it bleeds down. Nice. So I don't think there's anything wrong with this capacitor, with the power supply cap. Although this speaker cap is definitely bad. We're going to have to look at that. The other thing I want to take a look at is if we have anything. Yeah, we do not. Okay. And the next thing I want to check is I want to check leakage and ESR on these speaker caps, because I really don't want to connect anything and short out. You could see that one appears to be shorted. I don't know. Maybe not. So let me look at this, and as long as these are good, I think we can try to put a signal through it. All right, let's get Mr. Wizard involved. Move this out of the way for a moment. And let's check the first speaker capacitor, and it's excellent. Low ESR. Let's check the crusty one. Ha! It's reading good too. So at least from a ESR standpoint, the caps are good. But of course, until you check it for leakage, which I don't know about this, what that's going to do for us, but I have a feeling that might be a problem. But it might work enough for us to be able to test it. Let's just see real quick if the built-in capacitor checker on here will allow us to check the capacitance. These are supposed to be 2,000 microfarads. Whoop, sorry. 2,600 microfarads. It's reading a little high. When they creep up like that, that means they're starting to go bad. And that one's reading about the same. 2.6, so 2,600 microfarads. So even though you have that crusty leakage on there, the cap is still mostly functional. I think this might be okay to test out. Okay, main speakers, power on, volume down, set to the extra input, and I still have a 40-watt current limiting bulb in there just in case something goes bad and I don't have my microphone on. So you probably didn't hear anything I just said. All the controls are set. We're auxiliary input. We have a 40-watt bulb for our current limiting. Let's turn on and see what happens with speakers. No, that's not good. Yeah, I'm hearing shot noise. So we either have a bad connection somewhere or we have a bad transistor that's leaking. Okay, another phone call. So I'm thinking we either have a bad control or possibly a bad transistor, and being that we're not touching anything, I'm going to turn it back on. With only a 40-watt bulb, we're probably not going to do much more damage, and if a transistor is the culprit and it's going to fail anyway. So relatively low risk, other than making loud speaker noises, which I'm not worried about. And let's just move the controls and see if something like that is causing all that noise. So it's not the speaker, not the volume, scratch filter, rumble filter, that's noisy a little bit, tape monitor, selector, so yes, it's not a control, it is a transistor. So we're getting shot noise, and that's called shot noise. Take a listen to this. Okay, that is a textbook case of shot noise, I think. So I'm going to turn this off. And that could be because one of those capacitors is going leaky, getting out to the speakers, if you noticed that one. Or it could be, like I said, a transistor, but it's shot noise from one of those two things. So we have our work cut out for us now, and we're going to have to go through and try to troubleshoot the problem. Well, I was getting ready to connect a signal generator and the dummy load to this, and I flipped it over, and I think I found at least one of the problems of our shot noise. Yeah, we have part of a capacitor. And I think some of these have been replaced, because here's your two driver boards for the outputs. And you can see the capacitors they used here and then the ones they used here. So I think this has been serviced over its lifetime, but these capacitors are probably, at least some of them are bad, if not all of them. These caps don't always hold up so well, especially these plastic ones like this. Alright, before we start replacing things, why don't we snip this known bad capacitor out. Like that. And yeah, it's pretty bad. And let's just jumper in a substitute. This is a 50 microfarad at, what is it, 250 volts. So it should be okay. And there we go. All right. Let's turn this thing on, and we'll see what happens. I think it would help if I connect the oscilloscope probes first. Stand by. Okay, let's try again. Power on. And we still have a lot of noise in there. See that? Let's see what we get. Turn up some volume. We have one channel we have an output, but not the other. So we only have an output on one channel. So yeah, there's more problems than just that. Okay. Well, we're going to need to go through and do some troubleshooting. But we just can't leave all these caps in here like this. Well, let's check them, but I think they're going to be bad. And I just don't want to waste all my time replacing them and not know the original problem on top of that, so we could replace it also while we're in there. Okay, capacitor wizard. Of course, this one we know is bad. Dead as a doornail. I'll prop this up a little bit so you can see it better. There. So none of those will cause problems. That one's bad. How about this one? That one's okay. Okay. That one's open. Nope, that's good. I didn't check that one over here. That's good. Alright, so there's a bad one there. See, that one's good. This one is shot. So that's a bad one. That one's okay. And on the preamp tone control boards, these are all generally okay. I mean, like I said, even if they're not perfect, they're good enough that they're not going to give us too much trouble. That one's shot. See, that one reads a little bit. That one does not read at all. Okay, so this one's bad and this one's bad. But again, I don't know that those are going to completely block the thing from working, but that could be a coupling cap. We'll have to look that up, but okay. So we can check for some voltages. I don't know if I can get my meter in there, but we'll do that next. Okay, because of the way this works, the collector of one side of the output transistor should be at rail voltage. The collector of the other one should be at half the rail voltage if the transistors are turned on properly. So let's check the collector of this side. And you can see there's rail voltage. Check the collector of this other one. There's half. That's good. This one, let me see if I can get on it. There's rail voltage. Half. So the outputs seem to be biased okay. Let's check the collectors of these two driver transistors. Same thing. And they match, so that's good. We go to this one. We just have millivolts on the collector of those. And if we go over to here, there's half rail. If we go to this side, which I think is the base, 1 volt on base, and 1 volt on the base there. So these two boards match. Okay, if we go to here, that's good. So as far as our transistors go, they all seem to be just really quick check. They seem to be working okay. So really, we're just not getting signal to one of the channels. The other channel is very noisy. So again, I think this has to do with bad capacitors. We'll start with that. We also need to check the resistors and everything, but really it'd be easier to do that when we get the boards up and out of here and check them out. But good news is our semiconductors seem to be okay. All right, capacitors have been replaced, and the only bad one on these two tone control boards that's really bad is this one. It's reading almost open, and I don't know what position that is, but it may not make any difference. So these two boards have been recapped, and I have confidence that that's what it's going to be. So let's go back over to the camera, turn it on, and let's turn it up. And look at that, we got both channels, but one, the blue channel, has less amplitude, and the balance control is in the middle. So let's bridge a capacitor. Let me back up here. Let's bridge a capacitor across that bad one right here. Let me go get one and see if that fixes it. So hold on a second. Okay. I think that's a 2 microfarad, so here's a 2.2. All right, let's put that in there and let's see what happens. And look at that. The amplitude is the same, other than all the noise that I'm injecting into it. So, bad capacitor. So, the tone control board should be recapped as well. But the good news is the amplifier works. The line stage and tone amplifier have all been recapped. And now I removed the cover from the phono stage, which is kind of interesting. And of course we have another cracked capacitor up here. So we're going to go ahead and replace all that while we're at it. And just kind of clean things up. I noticed there's a couple of broken wires here. These are just, oh, I get it. These are just shields, so they're not being used. They're just twisted wires to add shielding. Okay, let's get these out and I'll recap them and try to do something with these boards that are kind of flapping in the breeze. Okay, we got the caps swapped out, and I put these little braces in here, these spacer blocks, and that really gave this a lot of rigidity and kept these boards from flexing so much. Cleaned all the controls, and I think the only thing left to do now is to replace these speaker capacitors, because they're kind of, that one on the top kind of concerns me a little bit, that it's leaking like that and getting that corrosion on there. So they probably should be replaced, and since I have them, we might as well do it. Well, as you can see, we have one of the speaker capacitors replaced already, and we're going to use one of these adaptacaps once again, and a 3300 microfarad capacitor. The old cap, which is pretty huge compared to the new one, was a 2000 microfarad at 65 volts, and I think this will work just fine. And these are kind of cool because we can just put this right in there and arrange it so that it fits properly, and it looks really neat. So that's what we're going to do with this one up here. Okay, the new speaker caps are in. I have it hooked back up. Let's turn it on. Let's see what we get over here. That's good, a good sign. And let's see if we get any kind of speaker action. Let me turn on the signal generator. All right, here we go. Nice. Of course, I have that bulb in there right now, but it seems to be working. All right, let's switch it over to full power. Let's see what we get now. Should be able to get a lot more. Oh yeah. Okay, let me change this a little bit. right. Different scale. I'm maxed out on volume, so this doesn't have a lot of gain in it for sure. Because I'm putting, oh wait a second, I'm going to put 1 volt RMS into the amplifier. See if we can, that should drive it to clipping, I would hope. Not quite. Yeah, there it goes. So we're getting about 25, 30 watts per channel. About, well, no, we're getting more than that. We're getting about 35 watts per channel. Let's put it in a little higher scale so we can see it all the way. Okay, here we go. So we can actually see when we hit the clipping point. Right there, we're starting to get some power supply clipping. So right about there. You can see the two channels are not perfectly balanced. We'll have to find out why that is. Could be the potentiometer, or it just could be that something, you know, something's not right with one of the transistors or something. Or we've really not checked the bias or any of that sort of thing, so we have to check that out. But by and large, it seems to be working very well. Now that we know everything generally works on this, and we haven't tested it extensively, but everything looks to be okay, let's look at the more unique feature of this amplifier. And this is pretty cool. Remember, this was a kit, and at the time that these things were being made and produced, most hobbyists didn't really have a lot of test equipment. Most of them didn't even have much more than an analog volt-ohm meter. So you really didn't have the tools you need to do a proper alignment or to check the output or check distortion or clipping or anything. And it's pretty cool that they put this feature where you can do all the alignments using this little panel meter on the front. And it serves multiple purposes based upon how you turn this rotary switch here. So what you would do is you flip the amplifier on its side like this. Hopefully I don't stretch all the wires. And when you look down here, there's a little, you can put your screwdriver in there to rotate that switch, and you can change the position of this switch, and it changes the function of that front meter. So you can do bias and balance and so forth for both the left and right channels, and then normally in normal mode you would put this switch in the middle like this, and it acts as kind of a rudimentary power meter. So we'll put the bottom cover on this so we can see that, and then we'll come right back and we'll follow the manual how to do the alignment as if we didn't have the test equipment. So now that we have the bottom cover on, you can see this silver tag that's adhered to the bottom of the cover, and you can put your screwdriver in there and you can rotate this switch to check your bias and balance, which is pretty awesome. So in normal operation you'd have it in this middle position, which is power monitor, and then they even tell you what you need to see on the meter. And that's provided, of course, that the metering circuit is working properly, which we're gonna use that process right now, and we're going to adjust it, and then we're going to take the measurements with an external meter to see if it actually works. And we're going to follow the instructions. But I've never really, some vacuum tube gear out there has built-in bias meters and adjustments, but very rarely do you see solid state gear like this that has it. So This is kind of a unique thing, and you know me, I like things that are unique rather than the same garden variety class AB stuff that you see every single time. So this is cool. Let's go through the process, or the procedure, and see if it will work. Okay, let's do the full alignment just like as if we built this thing. So you get to this initial test procedure, and they want you to set the thing on its side with the transformer side down, panel facing you. So transformer side is down. We'll rotate this. I have it on the Lazy Susan here, so we can spin it around. And what they want you to do is turn the bias adjust controls R11 on each driver PC board fully counterclockwise for minimum current in the power amplifier. So that's your bias. Turn the balance adjust controls on each driver PC board fully clockwise for the highest voltage on the plus side of the output coupling capacitors. Under the unit is the meter function switch. With the screwdriver, turn it to its normal position, power monitor. On the rear of the chassis is the initial test slide switch. This is the cool part, is this initial test switch. They want you to slide it into that position. So let's do this first, and then I'll get to what that initial test switch is. So there are two of these amplifier driver boards, one for the left channel, one for the right channel. And looking at the board layout, the bias adjust is this pot and the balance adjust is this pot. And if we look behind here, this is what we're going to see. So bias is going to be the right pot and balance is going to be the left pot. And if you recall, they want you to turn the bias adjust R11 fully counterclockwise. So we want these to go fully counterclockwise like that. And they want the balance pots all the way clockwise. So we want to rotate these all the way this way. Let's see if I can reach clear across the room. Ooh, that one was way off. Okay. So now we have our bias and balance pots in the position they want. And then they want us to switch what they're calling the initial test switch. So if we look down here, we have this switch that's directly above the power cord. And if we switch it to initial test, that's what they're telling us to do. Now, what does that do? This is the coolest part of the whole thing. Looking at the power supply, you have your AC mains coming in. And you have your power switch, which is right here. And when you're in normal operate mode, one leg of your mains just goes directly through the fuse and all that. The other end of your mains goes up through here, and it goes to the unswitched outlet, and then you have your power on, and then that turns on the switched outlet and the transformer for the power supply to turn the amplifier on. However, when you flip it into initial test, take a look at what it does. This leg is still connected, is now connected to this leg of your AC mains, and this is being disconnected from here. So you still have this leg going through the fuse, but this leg is now going through this side here, through the switch, and up through here. This is disconnected. So the only way that this leg can get to up here is through this unswitched socket. Why do you think they're going to ask for that? So in other words, you're putting this AC socket in line with this leg right here. If you just take a look at it for a minute so you can get a mental note of what it's doing. Under the unit is the meter function switch, and we read this part. On the rear of the chassis is the initial test switch. We read that part. Set the loudness, or the volume control, on the front of the unit to minimum position. So we've already done that. It's all the way down. make sure that the power slide switch is off, which I've done. Take the ordinary 15-watt electric light bulb and screw it into any handy table lamp. So they just want you to take a lamp with a 15-watt bulb, and they're going to tell you to plug it into a wall receptacle and turn it on to make a mental note of the brilliance of the bulb. So what they're saying right now, and luckily I actually had a 15-watt incandescent bulb. So I grabbed a little inline bulb socket here, and they just want you to plug it into an outlet and take a mental note of what the brightness looks like. So if you take a look, and the camera of course auto adjusts the brightness, but what we're supposed to do is look at how bright this. Now this is what the lamp would look like with full power, and this is what they're trying to get you to take a mental note of. Then we unplug it, make a mental note of the brilliance of the bulb. If you have an extra 15-watt bulb, you might also want to plug it into a wall receptacle and leave it on for a reference. So so you'd have two of these bulbs, so you could compare this one after we do what we're going to do with it to the one that's plugged directly into your mains. All right. For those of you who have 220 volt conversion kits, switch the line voltage, switch to the correct power line voltage, blah, blah, blah. All right. Making the initial test. Read these entire instructions first before starting, and this is why. There's things that later on you're going to read and you're going to realize you should have done it before you started all this. Note the position of the needle on the power monitor panel. All right, so let me move this out of the way and let's take a look. So we'll get the camera right on there. So you can see it's dead on 0 right now. Perfect. Okay, back to the instructions. And then they just have you adjust the panel meter if it's out. Power monitor panel meter, this is the 0 current, and it should agree with figure 24. So they're saying they want the meter to be there, and it was, right? There it is. Okay, and they're really picky about this meter, and you can read about that if you want. Here it is. All right, leaving the switch of the lamp on, connect the AC plug of that lamp into the unswitched red accessory outlet. I think you guys are starting to. Are you all figuring out what we're going to do here? So here's the red outlet. I'm going to plug this in here. And what does that do? For those of you who haven't figured it out yet, let's go back to the schematic for a second. And by switching this switch into the test position, you're now taking this leg of the lamp, or this leg of your AC mains, you're feeding it through here. Now you have that light bulb plugged in there. So you're putting that 15-watt bulb in series with your AC mains. What this is doing is this is a built-in dim bulb tester. Wouldn't that be cool if everybody did that? If all of the amps out there did that. That's just a simple, elegant test tool that you can use. I love it. Connect the amplifier power cord to any convenient outlet while watching the 15-watt lamp. Turn the power slide switch on. At first the light bulb will get somewhat bright and then quickly dim, and of course the reason it's doing that is because the main that filter capacitor in there is going to charge up. And once it's charged, it'll dim back down. Panel meter should read 0 current. If these conditions do not exist, then stop here, turn the amplifier off, and remove the power cord. So that panel meter, when it's in normal operating mode, it's actually monitoring the current in the power supply. That's why there's only one meter in a stereo amplifier. It's not looking at the speaker output, it's looking at the current going through the amplifier. The amplifier is now plugged in, just like they say. Let's switch on the power switch and see what happens. And as you can see, it got bright and then it dimmed, and it's not even half brightness. It's very dim. This is why they want a 15-watt bulb. If you noticed when we tested this thing earlier, I was using a 40-watt bulb, and that 40-watt bulb was so big of a bulb that it didn't even get bright hardly at all. It just flashed on for a split second and went totally dim. With this one, since it's only a 15-watt bulb, it's going to glow a little tiny bit, so you can see that there is quiescent current in the amplifier, but you can tell, if there's too much current. Now that we know everything's okay, they want us to turn the meter function switch to balance right channel. Meter should read somewhere between 3 and 6. So let's go up to here, balance right channel, which is this one click over this way, and we should look over here at the meter. I'll move that light out of the way, and it said that it should read somewhere between 3 and 6, and it's right on 3, just barely over 3. You can see that. They now want you to switch it to bias right channel, so that's the next click over. The meter should read 0 current. Turn the meter function switch to balance left channel, and we're just going to repeat the same process. So balance left channel, and you can see this one's about 5. Just has to be between 3 and 6. That's all they're asking for. And then bias, again, 0 current. Everything's good. This is what it should be. Now the reason they're having us do that is they wanted to make sure that you didn't miswire anything, number one, and number two, that you don't have a failing or shorted transistor somewhere. They don't want these transistors. Remember, back when these were made, these were the most expensive things in here were the transistors, especially the outputs. And this particular one, even though they were your ubiquitous 2N3055 NPN power transistors, it was a big deal because they were matched sets, matched pairs. And of course, you didn't want to have to go out and have to replace those, especially if you didn't have a parts store nearby. You couldn't just go on DigiKey and order them back then. So this was an initial safety test. So once we're done with this, and you make sure that it does what it says in the instructions, now we can go on and actually do the bias and balance adjustment. Now, since all those things tested out okay, they want us to slide the initial test switch back down to operate. And you can see I have the unit plugged in, and I'm on the unswitched outlet, and the bulb is now powered on because now it is a normal unswitched outlet. So you can see it's still plugged in here. All right, so you don't need a dim bulb tester for this unit because it has a built-in one. All you need is a lamp to supply the bulb, and you don't need anything else. Isn't that awesome? We now have full power on the amp since we slid that switch back to normal operate position. And what they want us to do now is they want us to switch our little function switch. We want the function switch to go back to bias right channel. And then what we're going to do is turn the power on, and essentially we want to make sure that we don't have any problems with the driver boards, and we don't have any leakage, because what's going to happen is if there's a problem, as those transistors begin to heat up because there's current going through them when there shouldn't be, this power meter is going to start to climb. Remember, this is measuring, technically it's measuring the power going into the power supply or coming out of the power supply, and it does that by looking at the voltage drop across a set value resistor, which interpolates to the current. And of course, if we know what the mains voltage is and we know what the current is, this kind of gives you a relative power reading on the meter. And the idea is, with everything turned all the way down like this, you shouldn't have any bias at all on the transistors, because there shouldn't be enough voltage on the base to cause current to flow between the base and the emitter. So you shouldn't be able, so there should be no current flowing between emitter collector, or collector and emitter. So this should stay at 0 volts. And that's all they're trying to say. So we're going to turn the power on now. And you can see, just like they're saying, it's 0 volts. Now the other thing they want to do is switch to bias left channel and just make sure that channel doesn't have any problems. And if we look, it's good also. Then it says to go back to the bias right channel and make sure the meter still reads 0. They're making us be very, very, very cautious. All right, this is kind of funny. If all of the meter indications are correct, then all of your worries about catastrophic miswires are over. And then they have a really good, all kidding aside, really excellent troubleshooting section at the end of the construction manual. Remember, this book, this instructions, is designed for somebody who built this amplifier, for a kit builder. And they don't know how much you know about it or not, so they're being very meticulous. So this is an excellent kit. All right. Turn the meter function switch to balance left channel. So we're going to do that now. So there's balance left channel. Turn the balance adjust for the left channel until the meter indicates 0 current. So you see that? So what I'm doing here, let's see if we can get the whole thing in the field here. I am going to get onto this pot, and we're going to rotate until we see 0 volts there. So here I go. You want it right about at that 0 point. It's pretty close. So this thing can even check the DC offset. Isn't that awesome? Now go to bias until the meter indicates 0 current. Turn the meter function switch to bias left channel. Okay. So now that we did the DC balance, we're going to do bias and adjust the control until the meter reads 1.5. So you can see 1.5 is going to be just right between 1 and 2. And I'm going to do that by adjusting this pot. Now this is your bias pot. So we're going to go here, and I'll zoom you in so you can see it a little bit better, because it's going to be hard to see otherwise. All right, let's start turning this up. And you can see there's 1. There's 1.5 right about there. That's just what they want. All right. Now we're going to do the same thing for the left channel. So we're going to go to balance left channel. And you can see it's a little bit out of balance, and we're going to adjust the balance pot for that channel for 0 volts again. Get it right on 0. Then we're going to move to bias right channel, and we're going to turn that up to 1.5, just like this. There we are. Okay. And once we do all that, it's ready to go, according to them. Isn't that awesome? And then we return the switch back to normal power mode, like that. And you can see there's just a little nominal idle power. Remember, this is not speaker power. this is amplifier power supply power. So you'll see as we use this, when we connect it to speakers, you'll see this will deflect like a regular power meter, but it's relative to your power supply, not to the speaker load. So you can't correlate that to how many watts is going into your speakers. So what exactly did we do? I know some of you like chasing electrons through schematics. So here's your power output. And we looked at this earlier in the video. Your rectifier, this is your main 70 volt source for the outputs. And then these are your semi-regulated power supplies, we'll say. And if you look, this is the switch. And it's essentially picking off the signals from, if you look up here, here's the midpoint of the amplifier from your outputs. So these are the 2N3055s. This is going out to the speaker. This is the coupling capacitor. Here's the emitter resistor right here, which is 0.82 ohms. It's very low. So you're going to have, you know, a voltage here, and it's picking off that voltage and just kind of running it through a little metering circuit through some resistors into the panel meter. Very ingenious. So you're literally looking at your midpoint where the, you know, and it's going to have offset on it based on the procedure that you're doing. So that's the metering circuit in a nutshell. And as you switch through, it can also check the bias or the DC balance by looking at the difference across here. And you can actually, they want you to set that. They're using a resistor divider, kind of, think of it as a poor man's Wheatstone bridge. So essentially when you have the voltage drop across here equal to the voltage drop of your resistors, it's going to be 0 volts and you have 0 DC offset, if that makes sense. Again, just a beautiful, elegant circuit they put in there to do that. Again, this is a single rail power supply amplifier. So that means that your midpoint is going to always be somewhere between 0 volts and the positive voltage. So it's always going to be a positive voltage here. And it's going to, essentially you're setting it so that this midpoint is roughly half of your supply voltage. So your B plus is 70 volts. Technically you'd want about 35 volts, plus or minus a little bit because of the losses in the components. But this is going to be about half of your rail voltage. Now the reason that we're doing that is because one half of this, so this transistor is going to handle the positive going waveform, and this transistor is going to handle the negative going waveform. So as we turn these two on and off, that's how you get your voltage swing. And the problem is, because you have that 35 volt offset, you need to isolate that, the DC level, from the speakers, because if you connected your speakers right here, they would be constantly sitting at 35 volts. And then the sound would be modulating up and down from 35 volts. But by putting this capacitor in here, this cap will charge. When you first turn the amp on, the reason you hear that pop on these types of amplifiers is because this capacitor is charging through your speaker up to that 35 volts. So once you have that 35 volt potential across this cap, the net that from here to ground is going to be 0 volts. And then the only time that this voltage will go above or below 0 volts through the speaker load is if the voltage on this side goes higher or lower than that 35 volts. So if the voltage goes higher than 35 volts, the capacitor will charge up to that voltage, and that charging action will take a current path through the speaker coil and to ground over here. If the signal swings negative, the capacitor will discharge, and you'll have your speaker load here, and current will flow this direction, and as this capacitor discharges to the reduced voltage here. And that's how this works. The capacitor charges and discharges through the speaker, but once it comes to rest, there's no DC current flowing through the speaker. That's how these types of amplifiers work. Now, the reason you don't need the capacitor in a split power supply is because you'll put a positive 35 volts here and a negative 35 volts with respect to ground. So this midpoint will always be 0 volts. And if these are both turned on equally, they're going to put equal and opposite voltages at this midpoint. So with respect to your common, it will always be 0 volts unless you drive one up, and one down. So what will happen in those ones is, as you turn this transistor on, you're turning this one off, and the differential between the two will go up and down. That midpoint will change. And that's how those work. And we did a little bit of an experiment with that on a couple videos ago on how that works. Now, when we adjust the bias pot, well, let's start with the balance pot. When we adjust this pot, we're changing the voltage here at this base. And all we're doing is we're setting where we want the midpoint to be here. So we want to adjust this to get half of your voltage. So technically, the other method to do this would be to take your voltmeter and measure this midpoint. So you would go from here to ground and measure it, and you would set it to be somewhere around 35 volts. So let's see if that procedure did that. Let's see what we have. The easiest way to measure this will be to just take our meter and clip the negative lead of our meter to ground, over here to ground, and then take the positive probe, and we're going to check the collector, which is the case of that output transistor. We'll put our meter on the case here, and we should see 70 volts. And if we have our DC balance set right here, we should see 35 volts, or somewhere a little less than 35, because again, you have losses in here. So let's do that. We'll go up here and we'll zoom out a little bit so we can see. And if I check, here's the cases of the two transistors. So if I look at, get a little light on the subject, right there, or not, there we go. So if I check this collector, you have your full DC rail, which is 69 volts. It should be 70 volts. Very close, isn't it? And then if we check the collector of the other one, we have about half, 34.4. So that procedure worked perfectly. But what I'm saying is we could have just as easily done that particular test this way and used the balance pot to set it that way. Now the bias is a little bit different. You need to have some quiescent current flowing through these transistors, even when they're in standby like this. That's the AB part of a class AB amplifier. So you want some current flowing through these. So what we're going to do is we're going to adjust the bias pot. That's going to change the voltage coming in here to the top of this, and this is going to turn on both transistors equally. So we're gonna actually turn both of them on a little bit so current begins to flow through them. And what we want is we want enough current to flow through the transistors that they're beyond their initial turn on. So we want more than we just want that 0.7 volt drop. We want to get through that so that the transistor is turned on, but we don't want it turned on so much that you have excessive current draw here. Okay, we want the speaker load to be the source of the current draw, but we just want this to sit on idling. If you don't have that, as you apply a signal to this, before these will start to actually move, what will happen is there'll be a little delay until that voltage gets up beyond that 0.7 volt drop, and this thing switches on before current starts to flow. And that's called crossover distortion. So this is just there to eliminate the crossover distortion from the transistor switching on to switching off. It's just always going to be a little bit on. But you don't want it turned on too far, because that's just wasted current, and current has to be dissipated as heat. So what's going to happen is if you turn this up too far, these transistors will just get hot, and that's not good for a transistor. So we want them to just sit at their basic idle point. We want them to sit at an ambient temperature that's just barely warm at all. And that's the proper way for these to sit at idle. So that's why sometimes bias is also called idle current. And the way we can measure that is we can measure the voltage drop across the emitter resistor right here, because the current in a series circuit is the same all the way through. So whatever the current is here, you'll have the same current here pretty much. So we can measure the voltage drop across either one of these, and we can use Ohm's law to determine what that current's going to be. And you're going to find out it's going to be in the milliamps, just a few milliamps. It's not going to be real high current. So let's measure it. So if we connect our meter from the emitter of this transistor to the collector of this transistor, we will be reading the voltage drop across this 0.82 ohm resistor. So I have the meter connected to the emitter of the top transistor, and if I go to the collector of the bottom transistor, let's go to millivolt mode so we can read it a little better, and we have 26.2 millivolts. All right, and don't worry about the minus or the plus. And if we take .0262 divided by 0.82 ohms, it gives you 31 milliamps. And like I said, that's a pretty good idle point for these transistors, is about 20. They usually run anywhere from 20 to 30 milliamps. And as we've seen in earlier videos I've done, you can sometimes reduce that a little bit and run the amp even a little bit cooler and still not get any crossover distortion. But it really doesn't matter. It was designed to work that way. So as you can see, the procedure in the book using that little panel meter is extremely accurate, and it's just as accurate as using your external test equipment. Okay, we have some speakers connected, and let's just turn it on and you'll hear that pop, and this is going to be the sound of the capacitors charging through your speaker. So here we go. You hear that little thump? That's what that is. Okay, let's see if we can cue up some music. Okay, we're going to use our Stranger Danger song that we use all the time. Let's try the loudness switch. Switch it off. Sounds pretty good. Now you can see one of the consequences of increasing the capacitance of these output caps. So you see these are 3300 microfarad. The original ones were 2000 microfarad. Believe it or not, it doesn't make an enormous difference You have to change the capacitance a whole lot to get a whole lot of change, but what it does do is in the subsonic range, the roll-off of the low frequencies is a little bit more gradual. What that's going to do is it's going to give you a little more subsonic sound, you know, that bass that you can feel and that warmth that you get. But the trade-off is a lot of power that the amplifier can supply is expended through those lower subsonic frequencies. So the amplifier won't physically get as loud unless you turn your bass controls way down. But you notice, even without the loudness switch turned on, we were still getting very, very deep, good bass response out of this amp. But being that it's only rated at, you know, maybe 35 watts per channel, realistically, it's going to bottom out very quickly. And if you noticed, as I turned the volume up, this meter really started to inch up towards towards being maxed out. And that's the result of that. If we would put those 2000s back in there, you'd have a little bit less of that subsonic bass. They did that on purpose for a couple reasons. Number one was most of what you listened to back then was on vinyl records, and subsonics causes a lot of rumble, especially in lower end turntables or not properly damped or isolated turntables. You do have the rumble filter, which basically just makes the roll off on the bass frequencies even more dramatic. So we do still have that to use, and we still can turn down our bass control. But if we want to hear that deep sound at low volume, those caps are kind of a good upgrade to do. It's really a matter of choice, and it does make an audible difference, at least if you have the speakers that can reproduce those frequencies. So everything depends on everything else, is what I'm saying. It's not just, you can't just make a blanket statement about it. But that was the choice I made on this, and those are the reasons. I think this thing sounds great. I think it would make a great kind of a bedroom amplifier, or a small, like if you have an apartment or something, you don't have a big listening area. If you had this coupled with a really nice set of efficient speakers, this would be a beautiful sounding system. So that's it for this video. I'm going to put the cover back on and give that a little cleanup and call this one finished. So as always, I wish you all peace, joy, happiness, and good health in your lives. Take care, everybody, and stay well. Bye-bye.